Hello there. I already posted this as a PDF, but I thought, you know what? I think I'll go back and narrate it and turn it into a video because I wanted to mention some things that aren't in the notes on the PDF. So what I did way back when, I think I did all this in 2013 when I owned a Helicycle, was I did some tests measuring fuel flow using a very capable multimeter that was able to capture and store data, and then I could graph it later on. So I want to go back and explain a little more than is in the PDF in case you're interested. So there are two functional blocks that control the speed of the engine. The first is the governor, which you see here, which is an analog circuit that has two inputs. One measures engine RPM, and the other measures the requested RPM from the pilot. And the way they work, the engine RPM uses a magnetic pickup that's very close to the flywheel of the engine. And the flywheel has some holes drilled in it at regular intervals. And every time a hole goes past the pickup, it creates a disturbance in the magnetic field, and that creates a pulse. And this pulse train goes in as one input. So that tells this circuit what the RPM is of the engine. The other input is the resistance of a potentiometer, which is on the end of a shaft that goes up through the collective and is controlled by the position of the twist grip, like a throttle on a motorcycle. So those are the two inputs. There's only one output. It basically compares the requested RPM from the pot with the actual RPM from the engine sensor and generates an error signal. So if there's a difference, then it's going to correct whatever current it's feeding into the fuel controller. So if it needs to reduce the RPM, it's going to reduce the input to the fuel control. And if we're going the other way and it needs more fuel, then it will increase the current going to the fuel controller, and I'll show you that in a minute. So that's it, two inputs, one output. Pretty simple concept. And there are 5 things that you can adjust: speed, gain, stability, droop, and idle. And I'm showing you a blow up of that area on the governor. You pull these plastic caps off, and there are little multi-turn potentiometers in there that you adjust with a little bitty flat-bladed screwdriver. I do not know the definitions exactly of what they have in mind with those, but I can guess. I would think speed is the full speed setting. Idle is the low speed setting, so that defines the range from high to low. Stability is self-explanatory, and that probably controls the time constant. In other words, how fast does this respond to differences between what's requested and what the engine's actually doing? I'm guessing because I don't have the manual in front of me. Droop, I'm less confident in making a guess on what that does. At any rate, I should have looked into all this in greater detail than I did, and I'm sorry that I didn't, because now I have no helicopter and I can't do it anymore. Initially, back in the day, people were having all kinds of unexplained problems with their fuel control. They didn't know what was happening. One minute everything would be fine, the next everything was going crazy. What was happening was interference in the form of what's called EMI, electromagnetic interference, was getting into the to this governor and creating all kinds of crazy responses from the governor, which was driving the fuel control nuts. And in one case, owner builder, apparently in front of his hangar, picked his helicopter up into a hover, and then he keyed up his radio to get hold of ground control to get permission to hover taxi out to the runway. Helicopter yawed about 90 degrees instantaneously, and the engine flamed out, as I recall. And instead of stopping and asking himself what just happened, he went, started the engine back up, got back in a hover, and did the exact same thing again. So hopefully people are a little more hesitant to do something like that. If something unexpected happens that could get you killed, common sense would say stay on the ground and figure out what just happened before you do it again. At any rate, what was happening, as I say, was electromagnetic interference was getting into the circuitry on the governor. There's two ways it can get in. It can go through the air in the form of radiated EMI, or it can be coupled into the wiring and travel through the wiring in the form of conducted EMI. Radiated EMI is dealt with by putting the electronic circuitry inside of a shielded enclosure. So the radio signals can't get from the antenna directly into the circuitry. They'll hit the shielded enclosure and they can't get in. Conducted EMI is a little trickier because in that case, the interference has coupled into the wiring, and it's going to come right in with all of the wiring. And so that little box you see in the upper left there is how I dealt with that. Every wire going in or out of this box goes through its own individual EMI shielded filter. And they're all in that little box, which is shielded. So everything inside the box we assume is dirty. And all the signals coming out the other side on those little pins that are sticking out have gone through individual filters and they're clean. So all the signals coming in are nice and clean. Put the lid on the box, you've now dealt with conducted and radiated EMI. Problem solved. Nobody else has gone to this length, and it's turned out that you can get by with a little bit less than what I did. But this is the ultimate solution. So that signal, think of it as an error signal. Any difference between what's requested and what the engine's actually doing creates an error signal, which then rides on top of the current that's going to the unit on the right side here, which I'll explain in a second. So it's either going to increase or decrease the current going into that thing. And that thing, whose name escapes me, but let's call it torque motor, consists of a coil of wire to which this current is being fed, and a permanent magnet, which I'm sure is affixed to the shaft running right up through the center of this thing. So that lever arm that you see sticking out that's hooked to the red Heim joint, it attaches to a shaft coming straight down. It's a spline joint. And so what happens is as you put a current through a coil of wire, it creates, this is a DC current, creates a magnetic field in the coil. That coil creates a magnetic field which is going to oppose the magnetic field of the magnet, the permanent magnet hooked to the shaft. And so the higher the current in the coil, the more it's going to push against that lever arm. Does that make sense so far? So obviously the Heim joint that's connected to that shaft goes to another one at the other end, which is connected to a second shaft which goes into the fuel control unit itself. You see that second shaft. And the whole thing is pulled towards the idle end of its range by that spring, which is on the very left side. And there's two mechanical stops, little set screws. One is idle. So if there were no current going through the coil, or the governor was shut off, the spring would pull the fuel control lever arm all the way over towards the left, and it would be laying on the idle stop, and that would be the minimum RPM that engine's going to produce at idle, where there's no input into from the governor. At the other end's another high-speed stop, same thing. So that's how that works. I think I've covered that. So my multimeter, what I could do is I could say, I'm going to put my my test leads across the output of the fuel flow transducer. And that thing had an impeller that was in the fuel flow line path. So as fuel went through, it would turn the impeller. The impeller had a magnet on it. Same thing. Here we have another coil and another little magnet. That's pretty common in electronics. Every time that magnet went past the coil, it created a little electrical pulse. And what I'm doing is I'm counting those pulses up, and every second this thing stores the count and resets itself. So every dot you see, those are 1 second intervals, and then by doing the math in Excel, which is generating these little plots, I can convert the number of pulses per second to gallons per hour, because I know the characteristics of the fuel flow sensor. They're published and well known. And so in this graph, what I'm doing is I'm sitting at full RPM in the upper left, and you can see how stable those readings are, 1 second apart. They're almost all identical. So I'm sitting at a fuel flow of about 9.6, something like that. Then I quickly chop the power down to flight idle. And the reason I was doing this is my hard stop set screw was set too low initially. And if I did that, the engine would flame out. And that's certainly something that you wouldn't want happening in flight. Say you had to initiate an auto because your tail rotor malfunctioned or something. The last thing you'd want is to, on top of everything else that was going wrong, have the engine flame out. So that's what prompted all these tests that I was doing. And what I found was there was a damped oscillation. And you can see that initially I hit a rock bottom of fuel flow at 5.5 gallons per hour at time 67 seconds, let's say. And then it oscillated to an all-time high, at least for those cycles, at 7 gallons per hour over a period of what? 1, 2, 3, 4 seconds. And then it overshot again, went back up, down, up, down, up, down, up. Finally, things stabilized way at the end at time 80 seconds at a fuel flow of, let's see, 6.25. So had I had more time and not gotten distracted, I should have gone further. What would really be interesting here would have been to do this exact same test again, but measure engine RPM. And I think what I would see if I superimpose those two plots over this same time period is engine RPM lagged the fuel flow because of inertia. And so the governor kept saying, well, it's still going too fast, so I'm going to decrease fuel flow even more. Well, it's still too fast. And it got all the way down to 5.5. And then it realized, whoa, I've overshot. Now the RPM's too low. We need more fuel. Crank the fuel up. Oops, too high. Go back down. And so it was basically out of sync with what the engine was actually doing. And I think maybe the stability control might have had something to do with that. Maybe droop. I'm not sure what droop did. And I don't have readily available access to the manual anymore for the governor, or I'd look it up. But those are the sorts of things that I really enjoy dealing with as an engineer. Something odd is going on here. What's causing it? And how can I understand exactly what's happening, and how can I correct it? But I never did. Too bad. I wish I had. In this graph, completely separate, I think I did this months later, this is over a 30-minute period, 33 minutes from start to finish, when I was hovering. And you can see that I hovered for about 20 minutes, which is a long time to sit and hover. And I finally got tired of that, so I put it back on the ground for a few minutes to probably just relax and unkink my arms and my shoulders and whatnot. Then I went back and hovered some more, and then came back on the ground, and that was the end of the test. And over that period, I calculated that at the burn rate I was doing, based on the time, that and given the average weight of a gallon of Jet A, I burned 54 pounds of fuel. And if you look closely, that trend line is sloping downward. So from the beginning of my hovering to the end of my hovering, you can see I'm burning less fuel because the helicopter's lighter. That's pretty cool. What is unexpected is how come these dots are all over the place. Every sample is in a different spot. So there's something else going on, which was unexpected. And it certainly didn't show up on that previous graph that I showed you. The next graph I'm going to show you is an expanded version of this same test. So this one goes from 280 seconds to 2280. What I'm going to show you is a little section of that, which goes from 840 to 880. So you can see that's going to be sort of in the middle of that first longer 20-minute period when I was hovering. And the reason this thing doesn't start at 0 seconds, you'll see at the end I've got to go through a number of steps to set all this stuff up and get my multimeter going and capturing data and saving it away. And so I did all that stuff, got that all running smoothly, verified it was doing what I expected. And then I velcroed the multimeter down and tied down the leads so they wouldn't go flying out the door, and got that all organized. Then I had to climb in and start the engine up and get going. So it took me 280 seconds to finally get everything squared away and actually start, not start capturing data, because it was doing that for 280 seconds. But that was all of no use because the engine wasn't even running, so it meant nothing. So I started this particular Excel plot at 280 instead of 0. So that explains why there's an offset. So why are these data points scattered all over the place? I've confirmed to my own satisfaction that the data is accurate from that first plot. If you look at how stable everything was at full speed before I chopped the power, they're all exactly the same. So I trust the data. This is telling me something I don't understand, but I trust the data. I don't understand why it's all over the map. So here we are again looking at that same exact run of the 20-minute period when I was hovering, but only a 40-second period. So it's expanded way out. And what you see is there's some other oscillation going on there that's like a 5-second oscillation. I didn't even realize that was happening, and I never followed up on it. So again, I really wish I had. One reason I enjoyed having a Helicycle was finding interesting things like this and then trying to figure out what caused them. And so I could kick myself for not having followed up on this. But it's too late now. I haven't had a Helicycle for a long, long time. And it's not because I didn't like it. It's because my eyesight went bad. And this is the last slide. I'm just showing you all the steps I had to go through to get everything set up, and then how I did the plot using Excel. And the only interesting thing probably in that is that trend line, which is you have a number of different kinds of trend lines you can do in Excel. This was a 9-period moving average. So that's what that trend line is. So that's it. This is just a little more detail added to the PDF that I already did. So hope you find it interesting. And if you're like me and you have a Helicycle and you have a multimeter that can capture data and save it away, and you felt the urge, I'd love to know what was causing all that and whether anyone else sees the same thing I did.